Disrupt the lecture schedule a little bit. I'm going to go off topic for a day. And it goes back to this question of equals never. Right? As I said, I can't just let this rest, so I'm going to address equals never a little more. Right? What I want to talk about is the following. I said, it's going to be hard to build equals never, and I want to talk about how hard it would be to build equals never. All right? Let's start by pointing you out to two very famous papers in computer science. They're two of maybe the most famous papers in computer science. One of them is called On Computable Numbers with an Application to the Entscheidungsproblem.
Yes.
Wissen Sie Deutsch? Nein? Okay, Entscheidung. What does Entscheidung mean in German?
Decision.
To make a decision on something. Entscheidung. Okay? And this is by Turing. It's actually the paper in which he introduced what is called a Turing machine. So it goes on for a little while. It's like, it's longer than a tweet, for instance, okay? And you can see it was received on 28th of May, and it was finally read on 12th November, so even back then journals weren't exactly speedy. They didn't have computers then, so probably shipping papers around. It's maybe one of the most famous papers in computer science. Like I would argue that this topic of the application to the Entscheidungsproblem is in fact the thing that makes computer science a subject in its own right and not merely a branch of mathematics. Okay? Now it's kind of obvious, like we have things that generate carbon and stuff, and mathematics doesn't. But this is really the sort of starting point of computer science. Except it's not really. Because you see, this was received on May 28th, May 1936. But before that, in March 1936, a guy named Alonzo Church had written also a note on the Entscheidungsproblem. Okay, and Church's article is actually like I'd show you the whole article. That's it, done. It's not even 2 whole pages. Like if you throw out the footnotes and stuff like that, it's like a page and a half. Okay, you could almost tweet it. And so the question is, what is this Entscheidungsproblem and what does it have to do with us? And that's what I want to talk about a little bit today. So I've gone off the schedule completely today. Today's class, it won't be on the exam, so to speak. But it'll be good for you. You don't know there are no exams. All right. So I want to talk about this question. So the problem, as I said last class, and this should take about maybe half a class, and then if we have time left, we'll talk about computer networks. How's that? Okay, because it's also related to something we're doing today. So this question of the Entscheidungsproblem, or the halting problem, as we call it in computer science, which isn't the same thing. It's a decision problem, but it's the decision problem of what is a decision problem? Well, so the real question is, to say that something is never equal to something else, as I suggested last class, right? I want you to imagine that there's kind of 2 tapes over here, right? And you're mutating values into the 2 tapes. And as I said to a few of you at the end of class, it's actually a little trickier. In Pirate, you can't change 2 different values at the same instant in time. Okay? So even if I had 2 programs that were making the same changes, it writes 1 into box 1 and then writes 1 into box 2, writes 2 into box 1, writes 2 into box 2, writes 3 into box 1, writes 3 into box 2, right? It's just like going forever, constantly writing the same values. There's still an instant in time when they're not the same value, right? The point at which box 1 has been updated and box 2 has not yet been updated. Okay, so already, like, you can't actually do that thing, where you sort of write the same values. But let's ignore that. That's sort of a Pirate detail. And if you had maybe a multi-threaded language or a software transactional memory or whatever any of those things are, which you'll discover over the course of your computing education, you could imagine making it look as if they instantaneously updated, right? For all the external world can tell, you can make them look as if they instantaneously updated. So that part is not what's interesting. The interesting question is really, how can I tell as a language implementer whether 2 things are going to be the same or not? Right? That's really what it comes down to. To say that something is equal never, that suggests that I have some way of knowing all of the values that something might have, and based on that being able to make a decision about whether two things will have the same value or not. Okay? Now, I want to show you something that happens in Pirate, just as a waypoint to there. Okay, so, okay, trivial function, right? Now, question for you is, we have how many equality relations now in Pirate?
3.
1, 2, 3, 4. 3? What 3? Yell them out. What's the first one you saw? Always. What's the second one you saw? Identical. What's the third one you saw? Equal now. Okay? So, the question is, what happens if I ask whether f is equal always to f? What is Pirate going to say? We hadn't asked this question, right? We talked about numbers and structures and all kinds of boxes and things like that. We never really asked the question for functions, right? So I should really ask this question for functions. What is the answer? So I haven't hit enter. When I hit enter, what answer? Okay, there's two different questions here, really, right? What do you expect it to produce and what would you like it to produce? Right? They may not be the same thing. What would you like it to produce?
True.
True? Everyone likes it to produce true? Okay. What do you expect it to produce?
True.
Okay, ready? Ready? Do you know?
I think so.
Okay.
Yeah.
Okay, error. Unhappy, right? So let me do this. What do you expect that to produce?
Error.
What do you want it to produce?
True.
You want that to produce true? Okay, so you would like it to produce true, right? Okay. How about this? What do you want it to produce? Oh, now all of a sudden we don't agree, huh? Where did your agreement go now? Why do some of you want it to produce true? What do you want to produce true?
Yes, so a function is an input and an output, and as far as the user can tell, these two functions are the same.
Appear to be the same. What do you want it to produce false? Yeah.
If you put in a list for X.
Ooh.
Yeah, I want to think of them as functions of numbers. Right? It's obviously intended to be functions of numbers. You still want it to produce false? I mean, they're not computing the same thing. They're computing in somewhat different ways. Right? It may be there's some weird corner case where multiplication by 2, like, I don't know, overflows and underflows, and God only knows what computers really do. And so Pirate takes the position that that's also not comparable. Okay? Okay. So, here's a question. What about this? Is f equal now to g? Okay. No, I'm not asking what Pirate will do. I'm asking you, what do you think? Is f equal now to g? How many of you think yes? How many of you think no? Any other answers? I would argue there's one other answer. Like, what does it even mean to ask that question?
Yeah.
F on its own is just a function, right? I mean, you can talk about whether the function f of 5 is equal now to f of 5, g of 5, or even f of 5 is equal now to g of 10. But f is like this weird opaque value. Remember, I even said that it's constructing closures? Like, what are you going to do? Start traversing the closure to figure out whether two things are equal? Like, equal now on functions as opposed to some other equality is kind of a weird question. It doesn't even quite make sense. Okay? Now what about this one? Are they identical?
No.
Okay. Well, what about f identical to f? That seems, That one is obviously true, right?
No.
What? What?
Oh, yeah, it is.
I mean, it's the same function, right? If we think about like what moment in time was it created at, well, there's the same moment in time that f was created as f, right? Yeah.
I just remember reading the prior documentation saying that if something's identical, it has to be always equal and equal now. So that would mean that it can't possibly be identical.
Oh. Say that again slowly.
I read the prior
No,
documentation.
so ignore the prior documentation
It's,
part.
it's
Think about what it's trying to say. There's a relationship between equality predicates, right? What's the relationship between equality predicates?
Identicality implies always implies now and now, and always implies now as well.
Okay, so if two things are identical, then they had better be equal always, right? And if two things are equal always, they better be equal now. But being equal now does not imply they're equal always, and being equal always doesn't mean they're identical. So wait, what is the consequence of that here? It could be that something is identical, but if it's identical, it has to be equal always, right? So if it's not equal always, if it's not even not equal always, but it's not even answering to equal always, then it sort of kind of can't answer to identical, right? So if it didn't do this, it would break other things. But there's actually a better reason why it doesn't answer to this question. And I won't get to that till the end of lecture. In fact, more about that. Forget networking. I'll talk about that at the end. Okay, so why is it that Pirate doesn't answer equality questions on functions? Okay? The reason is because, well, here's a design principle we adopted. This is actually different. This is a place in which Pirate differs from just about every other programming language I've used, including Racket made a different decision on this. Okay? So Pirate disagrees with Racket on this point. We decided that functions are incomparable values. So we don't say yes and we don't say no. We just say we choose not to. It's the Glomar response. You know, Glomar response. I can neither confirm nor deny. That has a name. It's called the Glomar response. It was coined back in the late 50s. There was actually it's a kind of interesting story. You should go look it up. GLOMAR. It involves like nukes and stuff. Right? And it involves the fact that when people sometimes confirm some things and say, I can't answer that, they've actually leaked information. And so the military realized that any answer at all leaks information. Sometimes if you start answering questions, and the times you choose not to answer questions, you leak information. And therefore you should never answer any questions. Okay, and this is why we can't have nice things. So what is it about equality? Well, there's actually a long sequence of steps that I can't really show you in class today because I have to explain the notion of reduction, and reduction's kind of confusing because it kind of goes the opposite direction you would expect it to and so on. So I'm going to leave that to theory of computation class. I'm going to ask you to trust me on the following question, that what it boils down to is I need to ask, does a function halt? Okay? That's the central question, and that was the Entscheidungsproblem. Right? It really comes down to, can I have the following function? Okay? Halts takes a program and some input for that program, and it produces a Boolean. Okay? So halts basically takes a program and an input, and it comes back with a Boolean answer that says, yes, the program will halt on that input, or no, the program will not halt on that input. Does that make sense? Okay. If I can produce, you'll have to trust me on this, if I can produce that function, I can also answer all the other questions. I can answer the question of whether two functions are identical, have the same behavior. I can also then answer the question of two functions don't have the same behavior, and I can have a thing that actually honestly answers equals never. Yeah.
If you can't compare the values, why can't you compare the memory reference? Because f is just...
That's identicalness, right?
Yeah.
Yeah, well, we just told you why identical can't work on functions.
Instead of the value, you just compare the same memory reference.
That's what identical does. But if I answer that question on identical, I have to answer it on all the other things, right? but it's a better reason why it doesn't work for identical. And I'll get to that reason at the end, okay? Okay, so there's two good reasons. One is if I answer it for identical, the chain of implication fails, okay? And there's another reason which I'll get to at the end. But even that doesn't answer the general question, right? Because take a look at F and G, are they identical? They're clearly not identical, but they have the same behavior. So checking that they at the same memory reference is not going to help me say that F is equal to G. Okay? So there's a more general problem that memory references do not answer. Yes?
Perhaps this is outside the scope of what you want to talk
You can ask.
But, and Aditya was like alluding to this earlier, but like math, for example, we say two functions are equal if their domains are the same.
Yeah,
They correspond
yeah,
to the same
yeah.
outputs. Is that similar to this?
So that's the idea we would like.
Yeah.
That's the idea we'd like. The problem is how big are our domains? Yeah. So here is a difference between functions in mathematics and functions in computer science. Okay? To a mathematician, if I say there's a function square, okay? So that's a function that has 0 goes to 0, 1 goes to 1, 2 goes to 4, minus 1 goes to 1, minus 2 goes to 4, etc., right? So there are many views of functions. You can view a function as a formula, you can view a function as a table, right? And that table to a mathematician is, how big is that table? Infinitely large. Now, in school, I'm sure at some point your math teachers told you, right, you can think of a function as a table, yes? Did you ever raise your hand and say, how big is that table? No, because you can't ask such questions. You probably get detention or something in school, right? Okay, but like think about that for a moment. Did they ever tell you about the space complexity of that function? How big that table is? Where are you going to write it down? How are you going to store it? You don't think about those questions in mathematics, right? You just take it as a given that that table exists in the sky, right? Like in Plato's brain or something like that, right? It's like a Platonic table, and that table just exists, which means if I need to know what f of 3 is, what do? I just walk down the table and I find the entry for 3. How long does it take to walk down the table and find the entry for 3? Does it take different amounts of time to find the entry for 3 and the entry for f of 1000? No, you don't even ask the question. You literally do not even ask the question. The question is kind of meaningless. The table just exists. It's pre-computed for all time, and you just go look up the answer instantaneously, or maybe it takes time. Who cares, right? Even the question of big O is kind of weird. If we could just assume the table of all the inputs and outputs existed, what's the big O of square? Constant. The big O of every function is constant. The time complexity is constant because you just look up all the answers. They've already been computed. The question of how long it takes to compute doesn't even make sense. But in computer science, we assume that functions are actually computations, and we don't just pre-compute everything and store it in the, in your iCloud or whatever. We actually compute it on demand because these things are infinitely large. So there's a deep difference in perspective between mathematics and computing in just even our representation, okay? And therefore, questions like equality, well, if I could represent the infinitely large table, and I can do infinite operations in constant time, then I can just compare those two tables instantaneously and I can get an answer. But I don't have the benefit of having an infinitely large table. Right? Pirate is slow for good reasons, but it's not because it's storing infinitely large tables. Okay? So it needs some other way of checking whether functions are equal, and that's what I'm really trying to get at. Does that make sense?
Yeah.
Great. Go.
Why couldn't we have defined some kind of equality function to take a restriction on domain and then say whether it's equal on that domain?
Well, so I'm not even assuming, I'm assuming that the input is type correct.
I was going off of what you were saying, like that taking a certain domain and a certain input. You're saying since there's an infinitely large domain, we can't do it. So why can't we?
Oh, so it's like a fixed number of inputs.
Yeah, like to have the user.
Yeah, but I want to answer the general question, right? Like when I'm building Pirate, I have to answer the general question, right? I mean, look, this is a perfectly good question. There are lots of variations on this question that I'm talking about, and they're subtle because some of them become decidable and some of them are still undecidable, and it's kind of complicated. It's pretty tricky, right? I'm trying to compress essentially a semester into about half hour, and as you might expect, things are being left out. Okay? Yeah.
In the mathematical squaring case, couldn't you make an argument for the fact that there is some big O time complexity for doing?
Yeah. I don't want to talk about math. I do not wish to talk about math here, okay? So what I want to do is I want to return to computer science. Yes, the question of what does that actually mean is a very interesting question, not what I want to get bogged down in today. I'm already like bogged down, right? It's like this is turning into like a, a land war in Afghanistan or something like that. I'm not going to do that, okay? Let's focus on this question over here, okay? Halts. So what I want to say, let's see what happens if I could actually produce a function that I want to build into my programming language, that given a program, or just call it a function, and given an input of the right domain for that function, comes back and tells me, will this stop or not? Okay? That's the problem we want to ask, what is the consequence of having such a function in our programming media? Okay? What is a way I cannot implement this function? What is a way, talk to your neighbor, tell me what is a way by which I cannot implement this function. You certainly should not do this. Five, 4, 3, 2, 1. We're back. What is a way in which I should not implement this function? I mean, there's probably lots of turkey-headed things you could do. What's one way?
You can't just like run the program.
You can't just run the program in the input, and why not?
Because if it doesn't
terminate, then this thing will never come back with the answer. What did we want to happen if the given function does not halt on the input? What do we want to return? False. But if I just run it and it doesn't terminate, I can't ever produce an answer. Okay? So we agree we can't do that, right? So we need something a little cleverer, right? We have to figure out what that cleverer thing is. Okay. So here is essentially the argument that Turing and Church both made. Okay? And this was central to the idea that they came to the conclusion that what Church had defined called the lambda calculus and what Turing had defined called Turing machines were actually identical in their computational power. They found that they could each express any computation written in one in terms of the other, and then they used their devices to come up with essentially this proof. And that's when they said, aha, they must be the same thing. And that's where something called the Church-Turing thesis came about. It's really a hypothesis that says, we believe that all computational languages are no more powerful than a Turing machine or the lambda calculus. Okay? Something you will explore more if you take computability and complexity theory. Okay, so here's the high-level argument that abstracts over both of their arguments. Okay? So let's assume that this function exists. We're going to presume that such a function can be built. It's got to be a little cleverer than just running it, right? And but people are pretty clever, right? I mean, they built like MacBook Airs and stuff, so they must be pretty smart. Okay, so now I'm gonna show you some new constructions. I don't have the time to motivate all of this, like where did this come from? But if you've ever seen Cantor's diagonalization, you might see some echoes of this. If you don't know who Cantor is, that's fine. Actually, by the way, I should say this. Total aside, Rick Schwartz is a math professor at Brown. He's amazing. He's like a research mathematician, but he also writes kids' books. And he gives public talks, and he's giving a talk series right now. I went to one the other night, and it was absolutely lovely. It was on infinity, and the way he explains infinity is in terms of like a farm with infinitely long animals and stuff, and it's really hilarious. And he actually did a version of Cantor's proof in there too. So go look for Rick Schwartz's public lectures. He's got one coming up on dimensions. What does dimensionality mean in mathematics? Rick is great. Go listen to his lectures. Okay, so this argument will have some echoes of Cantor, but I can't tell you what Cantor is, and I can't show you the relationship right now. But here's what's going on. What we're going to do is we're going to assume, this is our assumption, okay? The big assumption is that this function exists, okay? Given this assumption, we're going to build a new function, okay? So I'm going to build self of f, okay? This function is simply going to be I'm going to ask whether f halts, okay, when given as an input f as an input. Okay? As long as the types work out, I can do that, right? Now, the question of how do I type this is a very interesting question, which we talk about in 173. But anyway, so I'm going to ask whether f halts when given f as an input. Okay? Now, that's weird, right? F is a function that seems to take what as a parameter? Functions as parameter. But like you're adults now, right? In high school this would have been weird, but all semester long you've been programming in functions that take functions as inputs, right? So it's not shocking to you anymore that a function may take a function as an input, and so f is one of these functions that will take a function as an input, and so it's reasonable to ask whether f, when given f as an input, is going to halt. Okay? Yes?
Do you only run this on functions which take functions as input, or can you?
Oh, I won't run it on anything else. I will not make type errors. Okay? Good. Yes?
Don't you have to give a function to the second f?
Yeah, that's.
Give it F.
No. I'm asking whether f, when given, so my assumption is all of my functions take one input in the world. Okay? And they do whatever it is they do. Whatever they do, given that input, they go off and do it. Okay? So I'm going to now say, given a parameter function f, I'm going to pass f itself as a parameter. And it does whatever it does. Okay? But halts is a thing that will tell me whether it halts or not. Right? Maybe f just returns its parameter, right? In which case we're fine, right? It obviously halts, right? Maybe f calls f itself recursively inside. Maybe it does in a way that halts, maybe in a way it doesn't halt. Okay? So all I'm assuming is my programs, or my functions if you will, okay? My functions take one input, and I'm going to give it this thing as an input, and it does whatever it does on that input. Maybe it just returns right away. I don't know. Okay? But halts is going to tell me whether that returns or not. Okay? Good? So, the type of self is going to be, self is, it takes functions and returns booleans. Right? Good? Okay. Now, next step. I'm going to define another function. Okay? So op is a function that also takes functions and returns, well, we'll see what it does. Okay? So here's what op does. If self of f, right, takes that f and passes it to self. Okay? What is self going to return? A boolean, so it's going to return either true or false, right? So, if self returns true, op is going to go into an infinite loop. Okay? A little perverse, I know. Otherwise, it's going to halt with some nice sweet value like 0. Okay? So the critical thing is, what op does is, if self of f returns true, self of f is a function, it's always going to return a value. Right? So the word for this is a total function, it always returns. Total means it produces an answer for all inputs, it gives you an output. Okay? So halts we're assuming is total, right? That's our working assumption, so we can't write the naive implementation of halts because that would not be total. On non-terminating things would not return false, right? So it has to be total, it has to always return true or false. That's our assumption, that halts exist and it's total. Okay? So self is clearly then total because it just calls f on f, and halts is total, and all that self does is calls halts, so self is clearly total. Okay? So what is op? Well, op is not really total, right? Because op sometimes goes into an infinite loop and sometimes produces an answer. Okay? So far so good? Questions? I'm not asking you whether you could have constructed any of this. I'm only asking you whether so far everything on the board makes sense, like you can read the code that's on the board. Yes? Take that as a yes? Okay. Now, here's where the real sort of ninja move comes in. Okay? We now ask the following question. What happens? Remember, op takes functions. parameters. Op is a function. You can ask, what is op of op? Well, let's trace it through. Op of op is basically if self of op, then go into an infinite loop, else return 0. Yes?
So I'm a little confused. Like, how can you do op of op but not give the second op something else? Like, I don't know, because
Op takes one function as a parameter. I gave it a function as a
But
parameter.
then the second op also takes a function as a parameter.
This is like asking, okay, this is a little bit like asking the following. I have add1 as a function, okay? So add1 goes from numbers to numbers, and I'm going to say map of add1 over some list. And this is like asking, doesn't add1 take a parameter? You didn't give a parameter to add1, right?
There's other stuff in the implementation going on there which passes.
No, so what's going to happen? Map is going to be the thing that supplies add1 its parameter. Add1 is just being passed in. The same way, when I call op of f, right, it's going to pass. So when I call op of op, right, what's going to happen? Op is going to get passed to self, right? Now what's going to happen when I pass something to self? Well, we're about to find out, okay? So this turns into if halts. Well, halts what? Talk to your neighbors and tell me what to write here now. Go. Okay, everyone knows. Good. Okay? Halts of op, comma, op. I'm not calling the function, I'm just passing the function. You're 19, you can do that now, right? You just pass functions without calling them right away. Okay, so if that's the case, then I'm going to go into an infinite loop, else I'm going to return 0. Okay? Just by substitution. I haven't done any clever thing. Well, sort of, actually. I've done something very clever. Not I, somebody else did it. Okay? So, all I did was, let's trace this. I called op of op. Because op takes functions as parameters. Singularity, everything's a singularity function here. Op of op is if self of whatever my parameter, then go into an infinite loop, else return 0. Right? Okay. Now, what is self of op? Self is just halts op of op. So if halts of op, then go into an infinite loop, else return 0. Okay? Ha! The die is cast. Here's what? Let's ask the following. Op of op, does it terminate or does it go into an infinite loop? Those are the two possibilities, right? Either it halts or it does not. Let's say op of op halts. Okay? Then halts would have told us that op of op halts. It would have come back with true. That means we go into this case and we produce an infinite loop. That means op of op produced an infinite loop. Let's say op of op does not terminate. Okay? That means halts would have said op of op is false. Halts, sorry. Yeah, it goes to an infinite loop, right? So it'd say it does not halt, it would return false. If it returned false, we're going to produce a 0, but that means op of op produces a 0, that means op of op halts. Holy shit, what just happened, right? Here's what I'm going to ask you to do. Talk to your neighbors and trace this through for yourselves. Go. Go.
Or you can just take take the inverse, the opposite of.
Whatever is the weaker assumption.
Like, you're assuming Haltz works, right? That's the assumption. Then
A exists and B
it's not writing Haltz.
existing is a bigger, because you can exist without being found, so that's a bigger assumption.
So it's saying that basically you could have a Haltz function, but it would not work for all.
Which implies that it's not.
5, 4, 3, 2, 1. We're back. So, what just happened? What really happened is we showed some sort of contradiction here, right? What we showed is if op of op terminates, then op of op goes into an infinite loop. If op of op is going to go into an infinite loop, then it terminates. That's a contradiction. Okay? Clearly a contradiction. But what's the actual consequence of that? It can be easy because I've gone through so many things on the board now in a small number of characters, it's easy to lose the forest for the trees. Right? All of this only happened because I made a starting assumption. What was the starting assumption? That?
Oh, that it was total.
That what was total?
Oh, that Haltz was total.
Haltz is total. Okay? In other words, is that what you're going to say too? Yeah. That a function such as Haltz can even exist. If I give up on the expectation that Haltz is total, then everything else is just fine, right? I mean, there's no contradiction anymore. You just sort of run it and it doesn't produce an answer. So in one of these steps, it'll say, well, it doesn't always produce an answer, so it doesn't even matter, right? It's not a total function. So all of this only happened because I made the starting assumption that the function Haltz is total. Okay? Once I take that assumption off the table, all bets are off. Anything is possible. So this is the central idea, I would say, that gives birth to computer science as a discipline. Right? Even though it was proven by mathematicians, it says that if we assume functions are things that compute, then we cannot have a total Haltz function. There's a sequence of steps I would have to go from there to show you that given that there is no Haltz function, I also cannot have a thing that tells me whether two programs or two functions are equal, meaning they always produce the same answer. And then I can also go from there to say I can't have a thing that says that, well, I can't decide a question about, like, does it always produce the number 5? I can't even do that, right? And therefore, if I've got two boxes and one of the boxes is 5 and the other boxes is, I want to show that it never produces 5 or always produces 5, I can't decide that question either. All of these questions become what is called undecidable, okay? Where the word decide is used in a very specific technical sense. It means, can I have a function that implements it such that the function is total? The function always terminates and gives me the correct. It's easy if it doesn't have to give me the correct answer, right? It's easy to write terminating functions that are wrong. It has to be correct and it has to terminate on all inputs in the domain. For all programs, that is. Okay? That's what undecidable means. Undecidable means, for whatever property you say is undecidable, it means there cannot be a function that consumes all programs, always terminates, and is honest. That trio. Okay? Now there's 3 ways to break that. One is you can say, I give up on termination. One is I can give up on honesty. I mean, that one's a little weird. Okay? But it turns out to be very fruitful to give up on all programs. To say, maybe I can take a subset of programs. In particular, when you take computability theory, you'll learn that there are subclasses of all programs for which we can decide this. I actually, in my research with Tim Nelson, we work daily. We solve the halting problem on a daily basis. Right? We don't lie, and we do terminate. We just take a subset of programs. We don't take all possible programs. Okay? But what this means in general is all kinds of things that we wish we could show in computer science, we cannot show. As a person who writes compilers, it is a source of never-ending grief and pain to me that we can't decide whether two programs are equivalent. Because in essence, what is an optimizing compiler? An optimizing compiler is a compiler that takes your program, makes it faster. Well, we can make it faster pretty easily, right? Except there's a but. What's the but? We didn't change the meaning of the program, right? Otherwise, it's really easy to speed up programs. So, an optimizing compiler is one that takes your program and compiles it to an equivalent program that is faster by some criterion. It uses less space, less time, less memory, less, network, whatever, right? But I can never prove that that output program is equivalent to the original program. Now, there are ways we have, like in fact, one of the hottest areas in research right now is how do we prove that compilers are correct? It turns out compilers are sort of notoriously subtly wrong, and this causes weird bugs in programs. And so being able to prove that your compiler is not the source of errors is a really useful thing, because it's not like you don't put enough errors in there yourself, right? That your compiler should add a few more for you, right? So you want your compiler to be correct. And how do we prove correctness? Well, we always run up against this problem at a fundamental level, okay? So, that's the story of why we cannot have this kind of equality checker. Now, there's one thing I wanted to say. Is this on now? So, I want to come back nevertheless. So, okay, so does this make sense? Now you understand why equality checking is really hard? Equality checking is really hard because if we could solve equality checking, we can also solve the Haltz function. We can't solve the Haltz function, therefore we can't solve equality checking. Okay? That argument as to exactly why that is, I don't have time to go into. Okay? So, many of these questions, in fact, there's a very famous, really cool theorem called Rice's theorem. And it basically says, essentially any, I'm not going to define the word non-trivial, but it defines in a specific technical way, but it's pretty close to the intuitive way. Any non-trivial property of programs can't be decided. It's just like one theorem, it's like done, shut down the store, right? Any property you want to prove where it's like somehow it's, it's going to be true on a whole bunch of things and false on a whole bunch of things, that's what makes it non-trivial. Any of those properties is undecidable, like all of them, gone, right? So the only thing you can do is go to sub-languages of all programs, because on all programs, they're all undecidable. Okay? So is something never equal to 5 is then a trivial consequence of Rice's theorem because it's a non-trivial property and it can't be decided. Okay? So that's the reason why Pirate chooses to not compare functions at all. So here's the thing. Here's the problem. If you say f equals g, right? Is f always equal to g? So you wanted me to produce what?
True.
All of you wanted what?
True.
True, right? And you weren't too happy when it produced this, right? But think about the consequence of producing true for that. You want your equality predicate to say true when things are true and false when things are false, right?
Yeah.
Are you okay? Would you, okay, let me ask you this. Which direction would you like it to lie in? Would you like it to say true when things are actually false, or would you like it to say false when things are actually true?
False.
You want it to say false when things are actually true.
Well, 'cause I
So you'd be perfectly happy if the equality predicate just said false all the time. So it says false when things are false, and it also says false when things are true.
for functions.
For
Like,
functions. Oh, so for
like,
functions
if
you
you
want it
put-
to just say false. Well, then okay, then what useful info? No, great. What useful information do you get out of it then? It's just a constant. So there's no use then. Then it might as well produce error because it's not producing any useful information if it always said false. But that's not what you wanted. You all wanted to say true. I don't remember anybody saying I'd like it to say false. So here is the problem. Here's the tricky part about designing an equality predicate. Okay? So on base values, it's pretty obvious. And this is like one of the problems of being a PL designer. You have to think about all possible values, not just the ones that are convenient to think about. So when I get to functions, if I say that that is true, then I have to also be willing to answer this question. In fact, I have to be able to answer the question in general. And I just said you can't answer the question in general. Okay? So we can't answer that question at all. That's why we choose to not answer it for any cases, even the special cases. right? Because you can have other mechanisms for doing this, right? You can write some weird encoding of yours that checks it, but the language is not going to lie. Yeah.
What do other languages do?
So in fact, that's a very interesting question. They often use identical as the way of answering equal, which means that they will say true for f equals f, but then they will say false for f equals g. In fact, they will also say right? This one really looks like it should be, I mean, we're not talking about identical, right? We're just talking about sort of structurally equal. They are letter for letter the same. Well, except one letter, I guess, yeah. Okay? But they will say false because they're not at the same memory address. And that's pretty confusing. Right? And then there are languages that try to compare strings and then it's all over. Because when you have closures and you compare strings, it's dead. Right? It's just wrong. So, in fact, they will literally get it wrong because they're comparing strings. So, okay? So I want to answer one last question, which is why don't we say identical when why don't we just say, why don't we say this? Why don't we just say true? Because that at least is one thing we do know, right? And, I could say, f is not at the same memory location as h, right? Actually, here's the problem. It's wrong, it's problematic in both directions. I might, as a compiler, decide that f and h are actually textually identical, so I'm going to store them at the same memory location. So today, the optimization is on, right? Maybe in fact, in this case, because optimizers are really complicated and weird, maybe in this case they're stored in two different locations, but now they're stored in the same location. Maybe because they're next to each other, I have some optimization that's able to store them in the same location. That means you move your program up by one line, it went from producing true to false. You'd be okay with that? Tiny refactorings of your programs are going to basically completely change the output? Probably not. It's actually a subtler reason than that. Because the three designers, so Joe, Ben, and I, have also done a lot of work on computer security. And one of the things we work on is something called object capability security. And object capability security, here's what happens. You produce a function f from here, okay? Like the file system, okay? I want to give you the file system, but I don't want to give you access directly to the file system. So what I do is I wrap it in something else that monitors all the calls that you make. And if you call it the file I don't want you to read, it errors out. Otherwise, if you are well behaved, you would never know that you didn't get the file system. And I give it back to you as f. Okay? So, you have a thing called f that behaves exactly like the file system on well-behaved calls. And if you never make badly behaved calls, you'd never know. Okay? The problem now is if you have another way of getting this, you can now compare whether this and this are identical. But they're not. So what you've done is you've actually learned that I don't trust you. Right? And now you can behave well in front of me when you know you're not being trusted, and behave badly when you're not being mediated through me. It's a very big leak of information. It's really subtle, but it's a huge leak of information if you don't know that my mediation is transparent. And function equality is how you can leak it. So an object capability language never gives you function equality on pointers, because then I'm leaking information about what hiding I'm trying to do. That's the real reason we don't do it. Because we can't build a more secure language. Okay, last questions. I saw one or two hands go up, now the questions have gone away. Okay, good. Everyone, bye.